Okay, this will take a little while to get through, and your brain will probably be fried at the end of it, but hopefully you'll be able to go back and review this as we get through all these individual spectra. So there's a Spectra packet that I've posted online. It says spectall.pdf. It's got a bunch of background information where a lot of the images from this slideshow have come from, as well as a whole bunch of practice problems, which for those of you in lab, you will be doing those problems. So as a general review, we've got 4 primary forms of spectroscopy that we're going to deal with this semester. We've got IR spectroscopy, or infrared spectroscopy, which we have talked about already, and ultimately what we're looking at there are bond vibrations. So what we end up doing is exciting bonds, and those bonds vibrate, and we can detect that vibration, and we're all happy with that. Then we've got Mass Spec, which is a new one, and what's happening in mass spectroscopy is that we effectively destroy the molecule. And by destroy, what I mean is we effectively blow it up. And all those individual pieces, we analyze those pieces, and then we can thereby put our compound back together from mass spec. So it's kind of an interesting method. And then we have our carbon nuclear magnetic spectroscopy and our hydrogen nuclear magnetic spectroscopy, also known as our CNMR and our HNMR. These two, or particularly our HNMR, being probably the most powerful technique that you will deal with. Mass spec has a lot of information in it, but not as easily accessible to the layperson. Whereas the hydrogen NMR, you can pick up a little bit quicker than learning what's going on with mass spectroscopy, at least at a first pass. So we'll go ahead and jump right into this. So, solving IR spectra. What information does an IR spectra give you? Hopefully you can all remember this, particularly the way that I've been teaching it at least. We're looking at bonds, not functional groups. We can combine different bonds to come together to give us an overall functional group, but it's still just the bonds. So if we take a look at this sample spectra, you should be able to quickly go through and identify what bonds you see. Okay? So I'll give you a quick 5 seconds. You guys can go ahead and pause if you want to take a look at it. And now I will go through and label it. Hopefully what you see, we've got some CH-sp3s. So sp3 is in reference to the hybridization of the carbon. And then the rest of that is ultimately all in the fingerprint region. I wouldn't touch that unless I had some more information. So I would ignore that for the moment and hope that maybe I find something later on that can allow me to go back and look at that, because there are some nice peaks there. If not, oh well. Okay, so in hopefully less than 10 seconds, you've got something about your structure. Carbons and hydrogens. Kind of boring. Okay, so mass spec. And this does happen to be an example spectrum shown, and this is going to be for a particular compound that we've been about, or that we are going to evaluate. So remember what mass spec happens if, say, this is a horrible, completely non-politically correct analysis, but if we said we had a car, and that's my best representation of a car, and somebody put a bomb in that. Okay, well, one of the jobs of your effectively CSI investigators, or the equivalent of them, is to go through and find out where the bomb was initially located after the fact, find out what materials made up that bomb, and then where in the vehicle it was located. Was it in the car? Was it in the hood of the car? Was it in the trunk? And so we hire people that are very good at looking at these pieces and being able to put those pieces back together to determine all this extra information about the bomb. And that's pretty impressive considering the damage that can happen from these bombs. Well, mass spec is very similar. So what we're going to do is, instead of using a car, we'll take an individual small molecule, some small organic compound, and then we're going to blow it up. And in that blow-up process, what we're going to end up doing is removing an electron. So if we clear all of that away, we have, say, our molecule. There's a molecule. And it has electrons in it, and it's got a neutral state. Well, mass spec fires some kind of energy and knocks one of those electrons out. Okay, well, if our molecule has lost an electron, what charge does it become? Well, it becomes a mass of, or a charge of +1. And the mass is effectively the same. So after ejecting this electron, I can now determine the mass of this particle, and now I know the mass of my molecule. Okay, except it's not exactly that simple all the time. As we've discussed already, charged things are unstable. And so what ends up happening is not only does this single beam come in and knock an electron off, but now our molecule has the potential to fall apart. Okay, so it can break into other pieces. Those pieces are going to be determined based on stability. The more stable the piece, the more likely it forms, and we see that mass or that weight show up more frequently. So if we go through and now take a look at our sample mass spec, what we've got along the x-axis is an m to z, also known as a mass to charge ratio. Well, in the mass spec that we're going to be dealing with, we're only dealing with a charge of +1, which means when we look at those numbers represent the mass of something found at that particular weight. Okay? So we don't have to worry about charge at all anymore. It's just, hey, that's the mass. So nice and clean. The next part of this is what's going on the y-axis. Well, what we're monitoring is the frequency, or ultimately a way of looking at the stability of that individual particle. So the more stable that positively charged piece, the more likely that that compound forms. So when we go ahead and put our molecule into the sample or into the mass spec, we can't put in a single atom. We're putting in thousands, tens of thousands, hundreds of thousands, potentially billions or trillions of these molecules. Each one of those molecules has an opportunity to break and blow up into individual pieces. So what we're looking at is the sum total of all of those pieces, and ultimately our mass spec just sits there and counts. And so we've got an instrument that separates these pieces based on their mass, and so the instrument just detects then something hit me, something hit me, something hit me, and that was all at roughly 2 seconds. So it's going to correlate that 3 things that hit it as a slightly taller peak than if nothing hits it at 4 seconds. Kind of makes sense? So what we end up seeing is ultimately a separation based on the mass of each of our particles. So when we look at our spectra, probably the things that you would notice the most are kind of these tallest peaks. Okay. Officially the tallest peak, when we talk about it in lecture we'll deal with that more, but the tallest peak gets a name. But then the more important peak for us, at least as far as solving spectra is going to go, is what's known as the M+ peak. M for molecular ion. So what we're concerned about is the molecular weight of our compound. So the M+ peak means that it just lost a single electron. The weight is exactly the same as what it started. So if we can find the M+ peak, we now know the weight of our unknown compound. Okay? So where is the M+ peak? The M+ peak is going to be the largest molecular weight. So if we take a look at our signal furthest to the right, and then this is where it gets tricky, we're typically looking at the tallest signal within 3 units, within 3 M to Z's of the tallest peak. Tallest peak, or sorry, let me try that again. We are looking at the tallest, our tallest signal within 3 M to Z of the peak furthest to right. So if we go ahead and look at the very bottom of this, you'll see that there's a signal right there, okay, that I just kind of drew over the top of. So now I want to look at the tallest peak within 3 units. The tallest peak within 3 units ends up being this guy here. That is now our M+ peak, which also is now the molecular weight of our unknown compound. So to figure out that molecular weight, we've got 110, 9, 8. So the molecular weight of the unknown, in this case, is 108 grams per mole. which may not seem like a lot of information, but we can actually get a decent amount of information out of that number. Okay? But before we start pushing into the kind of mathematics behind this, let's take a look at one of the other secondary goals behind Mass Spec, and what I would actually argue is our primary goal. Because Mass Spec deals with the exact mass of the individual atoms that make up the molecule, what we end up seeing is a very strong isotope effect. Okay? So remember, there are certain, when we look at hydrogen, there's multiple different isotopes. We have different number of neutrons in them. So the hydrogen we're used to, hydrogen with a mass of 1, just has a single proton. So its mass ends up being 1. But then we could have a hydrogen that has a mass of 2. Well, it's still 1 proton, but it's now also 1 neutron. So now the mass goes up because of that extra neutron. Depending on the natural abundance of each of these isotopes, we might see a larger or smaller effect in our mass spec. Okay, so there's a lot of stuff on there, so let me go ahead and clear some of that away. So that isotope effect is really only going to play a big role for us with the atoms bromine and chlorine. Yes, we have an isotope effect with hydrogen and with carbon, but the natural abundance is something like 99% hydrogen 1 and 0.9% hydrogen 2. Alright, so if we look at a sample, yeah, we will see 2 peaks representing the difference between those two. But the difference in intensity for those is going to be 99 to 1. So we would have to see a peak that's 99 versus 1, which I can barely even draw on this. Being able to visualize that is just not that easy to do, and most of our compounds, being organic chemistry, are hydrogen and carbon anyway, so it's not very helpful. If we look instead at something like bromine, well, bromine is actually an interesting compound because there's 2 common isotopes for bromine. We've got bromine 79 and bromine 81. Well, what's the difference in those two? Hey, it's 2 units. 79 happens to be the most abundant. So if we were going to look at the most abundant molecular weight of our compound, that's going to be our M plus peak. Okay? If our compound happened to have a little bit of bromine 81 in it, we would expect an M plus 2 peak. So if we go up to the notation shown, you'll notice I've got an M plus to M plus 2. In the case of bromine, the natural abundance of the bromine 79 is something like 51%. And bromine 81, something like 49%. So almost exactly the same. So if we look at what I've described up at the top again, what we're saying is that the peak intensity of the M plus and the M plus 2 peak should be almost identical, should get the exact same thing. And if we go through and take a look now at our 2 tall peaks, we do have an M plus 2, and those 2 peaks are relatively the same. The conclusion from that is that not only do we have a molecular weight of 108, but we also know that bromine is in the molecule. Well, how many bromines are there? Are there 2 bromines? Well, we look back to the weight of bromine, there can't possibly be 2 bromines. That's because bromine's 79. We only have a total weight of 108. Okay? We'll come back to that again in a second. So we know there's bromine. Other elements that show this effect, chlorine, you can also pick it up with chlorine. You're again comparing the M plus to the M plus 2, and it's a 3-to-1 relationship. The 1-to-1 is really easy to see. 3-to-1 in most cases you can probably pick up, but it's not as easy, so it becomes slightly more difficult. Iodine, we don't really see an M plus 2 signal, but iodine is so big that if iodine is in our molecule, the molecular weight of our M plus is going to be really big. So you notice down here, we aren't even in the weight of iodine, so iodine can't be present. Another interesting feature with iodine is that it is so big that it is actually relatively stable on its own as I+. which I know sounds a little bit weird, but when it comes to mass spec, we can actually find and detect an I+ ion. So iodine cation can show up in the mass spectrum. The very last kind of quick and dirty thing that you could look at within your mass spec is that if you have an odd M+ peak, if that weight is odd, then nitrogen is present in an odd amount. It still has to be odd, because if we have two nitrogens, an odd and odd gives us an even. So an odd molecular weight means we have an odd number of nitrogens. So those are kind of the quick and dirty things that you would be looking for. So you're going to compare the M+ to the M+2, and if there's a significant comparison, you can go either bromine or chlorine. If you see a massive molecular weight, iodine is a strong possibility. And then if you see an odd molecular weight, nitrogen is likely present. So from that information, go through and clean this up again. Kind of clean all that junk out of the way. And in red, we've got our two pieces of information that we pulled from the mass spec. So the molecular weight came from our M+ signal. The M+ to the M+2 gave us that we had bromine. The secondary goal, it's up to you. I personally don't think it's worth the time, because I think other spectroscopy is faster and easier to interpret, but we can go through and determine a possible molecular formula from the mass spec. Well, what do I mean by that? Well, we know the molecular weight of the compound is 108, and we know we have a bromine present. So what we can do is take the mass of our compound and subtract the mass of bromine. What mass do we use? 79, 81, or the average? Remember, this is for the M+. The M+ was for our 79 for our bromine. And I'm horrible at mathematics, but it's a number less than 100. Oh, please don't make fun of me too much for carrying all my numbers. What do we get? 229? There we go. So 29 is now the leftover mass that we haven't accounted for with the bromine. Well, we can make some simplifications with this. The first being, this is organic chemistry. Primarily, we're going to have carbons and hydrogens in our structure. So what can we do with this? Well, let's figure out how many hydrogens there are. We could take 29 and divide it by the mass of hydrogen, which is 1. So I could have the formula H29Br. Does that make physical sense? No. Okay, well then, instead of dividing by the mass of hydrogen, let's divide by the mass of carbon. And when we do that, what we'll find is that we've got 2 point something something. I don't care what those numbers are right now, but not exactly 2. So that means there has to be 2 carbons in our formula and at least 1 bromine. Okay, so 2 times 12 is 24. I'm still missing 5 units. Those 5 units can be 5 hydrogens. Okay? This doesn't necessarily mean this is my molecular formula. This just provides me a possibility. In this case, it is, but if we had a lot more carbons, maybe that's not what we were actually looking at. Maybe we wanted something less than that. And so what we could go through and do is say maybe it's 1 carbon, and then the rest of that mass had to be gone into the hydrogen, so we'd have H17Br. So we increased our hydrogens by 12 units because that was the mass of our carbon. Is that formula physically possible? No. We can't possibly do that. Okay? So at the end of this, we have some bits of information here. We know the molecular weight, we know that bromine is present, and we know the molecular formula. For those of you that are really good at structure, yes, we could solve for the structure right now. Let's hesitate and not do that immediately. Let's see what other pieces of information we can pull out of other forms of spectroscopy. Okay? So, our primary goals from Mass Spec are highlighted up top. What we're looking at are those 2 primary deals and see what we can push from it. Okay? Next thing I want to address is that once you have the formula, and depending on who you talk to, they'll put a lot of importance in this or not. you can go through and calculate the degrees of unsaturation in your molecule. Okay? So we've talked about this when we looked at our alkane structures. We've got that general formula, CnH2n plus 2. So if I have a formula that we've already talked about, our C2H5Br, I can compare that to my alkane formula and see if perhaps there's any double bonds or rings as possible things within the structure. To go through and do that, you have to be able to convert your formula over into just carbons and hydrogens, which means you have to know some information about how to interpret heteroatoms, so things like bromine or oxygen or nitrogen. That interpretation is something that has always eluded me as a student, and I just think it's a waste of time to go through and do, but because I know it is something that people can use and it does provide you valuable information, we'll talk about it briefly here. So what we can go through and do is use this formula. Okay? You can already tell why I don't like it. It involves a formula and numbers. But we can use this formula to determine the degrees of unsaturation in our molecule. So let's walk through it. So what we're going to go through and do in the case of our formula, or our structural formula, is that we have 2 carbons. So it's 2 times the number of our carbons plus 2 plus the number of nitrogens. How many nitrogens are in our molecule? Well, 0. Minus the number of halogens. So that's our X is a halogen. Well, we've got 1 bromine. Minus the number of hydrogens in our formula. So in our formula, we had 5 hydrogens. We then add all those numbers up and we divide by 2. Okay? So 2 times 2 is 4, plus 2, which gets us 6, and then we get minus 6 over here. We'll get 6 minus 6 divided by 2, and we get 0, which means there are 0 degrees of unsaturation, which also means our structure is fully saturated. There are no pi bonds, there are no rings. Okay? It doesn't tell us what our answer is, it just tells us that those things aren't present. Yes, it's useful. Yes, you can use it. If the problem works out perfectly, it can shorten some of your work. If it doesn't work out perfectly, which oftentimes it doesn't, it was a bunch of extra work for nothing. Okay, so I'm not a big fan of degrees of unsaturation, but it is a useful calculation that you could potentially go through if you felt the desire to do so. Okay, so just be aware of that. You will see degrees of unsaturation when we talk about alkenes, so that will show up eventually on a test. It's not going to show up on exam 2. So the next part of this is HNMR, or sorry, NMR in general. So what we're dealing with in NMR is the spin of a nucleus. So we've been able to build instruments that can cause our nucleus to change its location or change its spin rate, and that's kind of neat. And the way I like to look at these is that we really have 4 pieces of information that we can pull from NMR. And they range in difficulty as well as far as the interpretation, so you need to be aware of those limitations. So those 4 things, and we'll kind of stepwise through these a little bit, is the number of signals, your chemical shift, integration, and then multiplicity, which you'll probably also hear me say splitting, but multiplicity, as we'll talk about, makes a little bit more sense. So let's start with the easiest to interpret, the number of signals. What that's going to tell you is the number of unique hydrogens or carbon. So if we're looking at carbon NMR, the number of signals can tell us our number of unique atoms. If we increase our difficulty a little bit, we can get into chemical shift. The chemical shift tells us the rough local environment of our hydrogen or carbon. So it gets us an approximation on where it's at. Okay, so what is it near? The next part is our integration, and this gives us the ratio of our hydrogens. Okay, so if we drew out an individual structure, say like a CH3. I know I shouldn't be drawing an example now, but I'm going to draw it anyway in the middle there. All of those hydrogens would be chemically the same, so we'd have 1 signal for those. Their rough chemical environment is that they're bound to a carbon, okay? And then the ratio, all 3 of these hydrogens are going to show up in the exact same chemical shift, which means that signal gets 3 times as tall as if there was only one hydrogen. So we can interpret some information from the amount of signal that we see. That said, it only applies to hydrogen. Okay, we won't use our integration information in carbon NMR. So really only the first 2 things can we use in carbon NMR, and then the last 2 are only applied in hydrogen. The very last thing that we can look at, which is significantly more difficult, is the number of different hydrogen neighbors. So it actually provides a lot of information, and you'll notice that most experienced organic students that deal with spectroscopy will jump straight into the multiplicity. And that's because they've worked so much with the number of signals, the chemical shift, and the integration that they can put structural pieces together very, very quickly in their head, and then add that last little piece of the multiplicity, getting that splitting pattern down to get that last section of structure. Please, 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 when you go through and interpret your spectra, you need to be going through in this kind of easy to hard interpretation. Okay? Start with your number of signals, then move to chemical shift, then integration, then multiplicity. Okay? If you jump around, that's when you're going to find it's going to get exceedingly frustrating because you're not going to be able to match things up appropriately. So try and go slowly through the interpretations, get the easy stuff down first. When it comes to the exam, I give partial credit. So if you jump straight to the multiplicity, there's no interpretation of any of the other data. I can't give you any points for any of that, and then you'll get the multiplicity wrong, so you get everything wrong. But if you start with the number of signals, I can give you or give you points for that interpretation. Okay? So start easiest and then work your way down. So, number of signals. This works for both carbon and hydrogen NMR, and what we're looking at is the number of unique atoms. In general, the way that I like to think about this is that if you built a model of any one of these 4 compounds, and then we pointed to an atom, either hydrogen or carbon, and we close our eyes and we flip and rotate, spin, throw the molecule on the ground, spin on it, stand on it, do whatever you want, and then when you open your eyes up again, can you point to that exact atom? Okay. If you can identify that exact atom with no questions, then that atom is unique. There's nothing else like it in that structure. If, however, you've got it confused with some other atoms within the structure, then all those atoms that are confusable are now chemically identical to it. So we would only see one signal for those. Okay, so let's take a look at a couple examples here. So in that first one, in our upper left, we've got 1, 2, 3, 4, 5, 6 carbons. So we're looking at hexane. And if we looked at just the carbons, and for some reason I decided carbon is going to be blue. So we look at that blue carbon on the end. Is it ever possible for me to get that that carbon confused with any other carbon? Okay, hopefully what you'll find is it looks the same as the one over here. Okay, so we would expect a signal that represented both of those carbons. So one signal representing those 2 carbons. If we continue to go through our structure, how about this carbon? Would I be able to get that confused with any other? Okay. Hopefully again, what we see is it over here. So we can go 1, 1, 2. It is different from the first one. Okay. And in the very last situation, right in the middle, 3, and we won't be able to tell the difference between that one. Okay. Sometimes people are really good at this. They can look at it and go, well, you could draw a mirror plane through the middle of that, and that's what's allowing for the equivalence across that. If you're that good, great. Otherwise, this kind of, if you spin, flip, or rotate the molecule, do you get it confused with anything else, seems to work pretty well. If we went through and did the hydrogens, so we cleared everything away, what we'll end up finding is the hydrogens are going to get a little bit more complex, but not that much more. If we try to identify those hydrogens and see them as distinct from each other, we would find that they're all the same. Okay, we can't tell the difference between them. So we could go through and label them as, say, the A-type hydrogen. Would we confuse them with any other hydrogens? Well, we confused the carbon at the end So that typically means that the atoms attached to it will also get confused. So all of these hydrogens would all be classified as our A type. Okay, we could then go through, and I'll color code it this time. We've got a B type in purple, and we've got a C type of hydrogens in orange. So we would have 3 signals in our carbon NMR and 3 signals in our hydrogen NMR for each of these equivalencies. Okay, hopefully that kind of makes sense. So I'll give you a second here to go ahead and pause. Not quite yet, don't pause. Take a look at this next one. So now go ahead and pause and tell me how many hydrogens there are. So pause. Okay, we'll come back to it now. How many different hydrogens do we have? Well, that for sure is unique. Do I have any hydrogens at that position? Nope, so we don't have to evaluate that one. We do have a hydrogen coming up here, which is different from our first one, but it's the same as the hydrogen over here on the opposite side. Even though they're both attached to different carbons, they're still chemically the same. And that's because they are both one bond away from this substituent. If we go through, we should also find hydrogen, hydrogen, one difference, and then we've got that last hydrogen out here. So if I was really careful with the color coding, we would have 4 different types of hydrogen within that structure. So hopefully both that one and the hexane were relatively straightforward. So now let's shift to 2 more challenging ones. Alright, let's take a look at the cyclohexane. Alright, how many different hydrogens are on that structure? Well, each carbon, again, has a hydrogen on it. Those look all relatively the same. So one first pass at this is that we might very well say that all of those hydrogens are equivalent. Those of you that I'm sure were really, really good with your practice are those positions the same? Is my purple hydrogen and my red hydrogen the exact same? If they are, there's no energy difference between those. And hopefully what you do remember from chapter 4 is that purple hydrogen is in the equatorial position, which is more stable because it has more space. So our red hydrogen is actually higher energy. That means there are 2 different types of hydrogen within this structure. Okay. Let that sink in a little bit, because I know you're going to think of an exception. What's that exception on this? What is our ring constantly doing? The bonds within that structure are constantly rotating. We are going through a chair flip all the time, which means that hydrogen that is equatorial is also becoming axial, and that hydrogen that's axial is shifting into the equatorial position every so often. So on an average, as long as that we have enough thermal energy to allow that cyclohexane to move around, we would see 1 signal for our hydrogens. If, however, we freeze the sample and prevent the rotation, okay, or the ring flipping, we end up seeing 2 hydrogens. Kind of a neat little distinction to look at there. So we can actually see the difference between our chair conformations using spectroscopy. Kind of cool. Okay. And then the very last one, which we will continue to talk about. How many different hydrogens are in that one? There is a CH3 out here, and a CH3 out on the other end. Can you tell the difference between them? Hopefully you say yes. One is connected to a CH2, the other one's connected to a carbon with chlorine. So that we got 2 types there. Then we have what appear to be 2 types there, or sorry, a type there. And then we have another hydrogen out here. So the general person would say there's 4 different hydrogens there. And I hate to be the bearer of bad news, but because of the chiral center there, okay, because we have a chiral center right here, the hydrogens on that carbon, one is wedged 1 is dashed, we cannot physically rotate about that bond to get those hydrogens to be exactly the same. Okay? This is something that you need to be aware of when it comes to your online homework. It's not something you typically have to worry about when it comes down to solving full-on spectra that you'll see in this class or on the ACS test. And the reason is that difference is not usually enough that when you go through to try and solve the spectrum that you see them shift away from that point. Okay? Their chemical shift ends up coming out the same. So while we have technically 2 different types of hydrogen, so in this case we've got 1, 2, 3, 4, 5 hydrogens on here, or 5 unique hydrogens. When we looked at the actual spectra, we probably still only see 4 signals. And that's because our purple hydrogens aren't different enough to show up different enough on our spectra. Just like when we looked at our cyclohexane, our axial versus our equatorial hydrogens typically don't show up different enough to actually see a difference in our spectra. Okay? So, just some things to consider when you go through and look at your NMR. So, try and identify the number of unique signals or the number of unique atoms within your spectra. Next thing to look for is your chemical shift. This again applies to both carbon and hydrogen NMR. This should be treated as simply as you would IR. So very, very fast interpretation. Try to not overinterpret this. In general, what ends up happening is that if we have a hydrogen or a carbon in electron-poor environments, they shift to a larger frequency. So that's what this table is trying to show. Notice the frequency gets bigger as we have less electrons around our atoms. Okay? That's typically referred to as de-shielded or downfield. I never seem to remember that, so I don't expect you to remember that, but just kind of be aware. For the most part, you won't have to worry too much about this general application, because just as we looked at in IR, there's very characteristic ranges for things with an IR. There's very characteristic chemical shift ranges within carbon and hydrogen NMR, and in most cases, you don't need to really stress on this, what's going on exactly with these frequencies, okay? Being electron poor or electron rich. Okay? So again, be aware of that. The more electrons around an individual nucleus, the smaller your values will be, the smaller your chemical shift. The less electrons around it, the higher the values. Okay? So, what are those values? When we're looking at hydrogen NMR, the range that we're going to look at, our chemical shift range, starts at 0 and it caps out about 14. You might see a little bit higher than that, but pretty rare. And you'll notice that I went through and labeled individual ranges within that spectrum, or within that line, of what you would expect to find in different ranges. Probably the most important distinction to make here is this 2 to 6 range, where I've got labeled everything else. When you look in your textbook, they will go through and list a whole bunch of different things that show up in that range. The problem is that everything shows up in that range that's not characteristic. It's like trying to read the fingerprint region to evaluate your overall structure. Okay? It's just not that helpful to do. Okay? So when you look at it, if you see a signal within your 0 to 2 range, you're looking overall at alkanes. 6 to 8 range, you're looking at an aromatic hydrogen. And notice that that is aromatic. We're looking at a benzene ring there. Okay? Right about 10, you'll see an aldehyde hydrogen. Carboxylic acids go all the way up into that 12 range. Okay? We carry this back to our overall term. We said protons in electron-poor environments shift to large chemical shifts. Well, how many electrons are around the hydrogen in that functional group at the end? All right, let's try it again. What functional group do we have there? It's a carboxylic acid. Acid free up what? H+. How many electrons does H+ have? None. So of course its value shifts to a really high frequency because there are no electrons around it. Okay, so we can see that general trend showing up there. If we were looking at carbon NMR, the range that we would be evaluating is from that 0, again, up to about 200. And I would say there's even less things to look at when you're looking at your carbon NMR. And oops, some of this wasn't supposed to show up. I would simplify your aromatics and alkenes and instead refer to these as pi bonds. Any idea why I would simplify it that much? The alkenes and the aromatics fall in the exact same range. Okay, so you're not going to see a distinct difference between, if you find a signal at 125, that could very well be just a double bond, or that could be an aromatic ring. Okay? Without more information, it's really hard to tell. Okay? So your carbon NMR, even more simple than your hydrogen NMR. You know where your alkanes are, pi bonds, and then carbonyl. That's it. Okay? So you should have these ranges memorized. If you do not memorize these ranges, your life will be hell when it comes through to try and interpret these things. Okay? It's not that much. In sum total, it's almost exactly the same as we had for IR. Okay? And because there really isn't anything more to it other than just seeing something in that range, we'd now move on. Integration gets a little bit trickier. So what we're looking at with an integration is the ratio of hydrogens. Okay, so every hydrogen is counted in an HNMR. Okay, so our signal will stack. And then you have to again remember that it only provides a ratio. So if we draw a sample spectrum, okay, so let's say this is 0 and this is a number. I don't really care what the number is. And I look at the structure CH3, CH2, OH. And I want to see how this is going to stack. So first off, let's do some interpretation. What is this oxygen going to do to our signal? Well, it's going to give it a much larger frequency. So if we go through, we've got that hydrogen is chemically unique, those hydrogens are chemically unique, and then these hydrogens are chemically unique. I would expect the blue hydrogen to show up furthest to the left based on our chemical shift. Then I would expect the purples, and then I would expect the oranges. Okay. Well, remember, in hydrogen NMR, every single hydrogen is counted. So if we go through and look at this structure, let's assume there's just one molecule there. How many blue hydrogens are there? Okay, there's just one. Whoops. Let's get that color right. One hydrogen. How many purple hydrogens are there? 2. And our orange hydrogens, there's 3. Well, our signal is only going to be as tall as the number of hydrogens counted. So in the case of our blue, we've got 1 signal. In the case of our purple, there's 2, because there's 2 signals. There's 2 hydrogens. And in the case of our orange, we would expect 3. Okay? So this assumes that we started with 1 molecule. What if I start with 3 billion molecules? Well, we're not going to have exactly 1 signal, 2, and 3, but what we will get is a ratio out of this. Okay, we might expect 1 billion to show up here, 2 billion here, roughly 3 billion here. So what we're expected to go through and do is look at the smallest whole number ratio and interpret that. So what we would see more often than not is a 1, 2, and 3, and what we're saying is that that is the ratio of hydrogens through this structure. If there was symmetry in the molecule, that means there's more hydrogens hidden somewhere that we didn't quite account for appropriately. Okay? And that's a little bit trickier to manipulate. I can't quite do it with this structure, but we will look at an example of that towards the end of this. Okay, so it only gives you the ratio. And it's looking at ultimately, one conclusion is your peak height. So how can we see our integration? We're looking for peak height, which is an awful way to do it. It doesn't officially work because remember, if our hydrogen can come on and off the structure, like in the case of an acid, it's going to have a bunch of different chemical shifts. So instead of showing up at an exact identical chemical shift, we have a broad peak. So we don't want to look at just the peak height. What we want to look at is the peak area. How do we calculate the area of a peak? Oh, good job. Look at that. We're looking at the integration. Okay, and we look at actual spectra, you'll see how that information can be given to you. But that's ultimately what we're looking at here, is the area underneath the curve. They must be mathematically calculated, usually by the computer, not by us. The very last thing, like I said, it's the most difficult. Our two big concepts are our colored ones there in blue and red. What we're looking at is revealing some information about neighboring hydrogens. So first off, what is a neighbor? A neighbor must be different from our source hydrogen, so when we go to evaluate, we'll always pick a single hydrogen to evaluate from, and then we'll see how many neighbors it has. Right? So those neighbors must be different from it, so it has to be chemically different, and they are usually found less than or equal to 3 bonds away. Okay? And I say less than, but in most cases you're looking at a 3-bond rule. Okay? And again, we'll classify that here in just a second. The result of this is that the number of peaks we see representing our source hydrogens will be equal to the number of neighbors plus 1. Okay, so let's go back to that ethanol structure that we were looking at. And I'm actually going to go through, color it out this way. So, how many neighbors does this hydrogen have, a boxed hydrogen? Well, this hydrogen, let's kind of underline them in red, those two hydrogens are chemically the same. So all those hydrogens are ultimately living in the same house. You don't refer to your roommates as neighbors. Okay, so those don't count. So while they may be 3 bonds away, or within that 3-bond rule, they aren't different. Okay, so we won't count them. So let's try that out again. So 1, 2 bonds, I'm at a carbon, 3rd bond, let's color those in black, I guess. 3rd bond out, I'm at a hydrogen. Is that hydrogen chemically different from my boxed hydrogen? Yep, that counts as 1 neighbor. Let's go back and count out our 3-bond rule again, this time in purple. 1, 2, 3 bonds. Am I at another hydrogen? Yep, also counts as a neighbor. But it's not different from the other one I circled. Well, the analogy I use here is that think about your neighbors. Do you have the exact same relationship with each of your neighbors? You probably have something slightly different, some different way to interact with each of those individual people. Hydrogens are doing very much the same thing. Okay? So while the red hydrogens might be chemically unique or the same as each other, they're both different from our black hydrogen, so it's going to see them both as neighbors. Okay, so what we have are 2 hydrogen neighbors so far. Let's try out our count rule again, this time with orange. And where we end is with oxygen. Is oxygen a hydrogen? No, so we don't have another hydrogen neighbor. But what about the hydrogen at the very end? Well, that is 4 bonds away. 1, 2, 3, 4 bonds. Does not count. Okay, we have to be less than 3 bonds. So our black hydrogen sees 2 neighbors. So if we try to figure out the number of peaks for our black hydrogen, will equal our number of neighbors, 2 plus 1, we expect to see 3 peaks. Okay, well, what about our red hydrogen? Number of peaks. Well, from our red hydrogens, hopefully what you'll be able to now see is that we see all 3 of our black hydrogens as neighbors. And you might also count out 1, 2, 3. We might consider that last hydrogen. It turns out when we're dealing with splitting that atoms like oxygen and nitrogen will hide hydrogens. That means any hydrogen bound to those atoms cannot act as a neighbor, okay? Even if it's within that 3-bond rule. So what ends up happening for our red hydrogens is they only see 3 hydrogen neighbors plus 1 gives us 4 peaks. How many peaks do we get for our blue hydrogen? Okay, well, as we just said, it can't see any neighbors. So it has 0 neighbors plus 1, we expect 1 peak. Okay? I know, it's a lot more complicated than any of the other things. It does involve a little bit of math there, but it does, again, give you a lot of conclusions about your overall structure, so it can be very, very helpful to deal with. Okay. Last thing that we should talk about before we move on and get back to our original example with our C2H5Br is how these peaks show themselves. Okay, so with one signal, we're just going to see 1 peak. There isn't really anything there. But what happens with the 3 and the 4? Well, it turns out when we do this multiplicity or this splitting pattern, what we end up seeing is very characteristic and symmetrical peaks and peak shapes, and that's what that diagram is trying to show in the left corner. So if you have 0 neighbors, you get 1 peak, and as far as its shape, there's nothing to compare to, so it just has an intensity of 1. If we have instead 1 neighbor, now we get 2 peaks. So this is our 2 peaks. The relationship of intensity, so how tall each of those peaks are relative to each other, is the exact same, 1 to 1. What happens if we move up? Let's jump up really high up there, up to 3 neighbors. We now get 4 peaks, so we can see each of those 4 boxes representing our 4 peaks. And if we look at the intensity between these, our peaks on the outside will have an intensity of 1, while the interior ones will be 3 times as tall. So what we end up seeing is something like that. Okay? For our 2 neighbors, it's typically something along those lines. For 4 neighbors, okay, and this pattern continues on. So if we have 5 neighbors, we still get the same kind of pyramidal organization of these peaks. Okay, and yes, we can get up to 8 neighbors potentially. That might be a bit high. 6 or 7 neighbors, and in that case, we have so many different hydrogens that it becomes very difficult to interpret each of these individual little peaks. Again, one of the reasons why multiplicity is more difficult to evaluate and interpret. Okay? So, hopefully now we can actually go through and build our spectra. So getting back to our overall problem. In this case, we're going to take a look at the carbon NMR for the compound that we've already evaluated some spectra on. And I'm going to stepwise through this into slowly revealing information. Remember, with NMR, start with the number of signals. In this case, within our box, how many signals do we see? I only see 2 lines. So what I would evaluate and expect you guys to write on your spectra would be 2 unique carbons. Okay? Yeah, I know that says unique carbons. You're just trying to get some information there, so as a grader, I have something to do. Okay? Make me work. The next part of this would be looking at the chemical shift. You'll notice that we haven't seen it yet, and that's because, again, I'm trying to get you to go through this very slowly. Because it's carbon NMR, that chemical shift will be 0 to 200, so we can add that in there. With that extra information, what do we end up seeing? Okay, well, our 2 peaks show up less than 50. We can go back to, or have already memorized, that general range, and that range says that those 2 types of signals need to be alkane type. Okay, that's it. That's carbon NMR. That's really all I would expect. Okay, so let's actually put up the real spectrum. The actual spectrum, you'll notice there is some differences in peak height. In carbon NMR, we really don't want to worry about that completely, and I'll talk about the exception in a second. The other thing that we might see in carbon NMR is a triplet of, or 3 signals all stacked up right around each other, about 77. That is due to the solvent. To run an NMR spectrum, we need to use a solvent to kind of keep everything moving. That solvent should be very minimal as far as the spectrum goes. You might see it on there, you might not, depending on the individual sample you're looking at. Okay. Back to the peak height. Peak height is ultimately related to integration, and integration is really only something we can do in hydrogen NMR. However, the peak height in carbon NMR is often correlated to the number of substitutions on the carbon, so non-hydrogen things present. The shorter the peak, the more non-hydrogens there are. So if I looked at a compound along these lines, that center carbon, now my blue carbon, I would expect to have a very short peak. Okay? It's just short because there's no hydrogens attached to it. Okay? If you want to think about it, you could say it's hidden if you wanted to. Okay? Very small nuanced effect. Sometimes it stands out really clearly and it can help you analyze, sometimes not. So just be kind of careful around that, but if you want to do it, you can think about that. So again, let's clear this all out. If I was going to grade this, full credit, what I would expect to see, 2 unique, I would probably even just be okay with 2 C's, and then alkane. Come on, alkane. And that's it. That would get you full points as far as the carbon NMR goes. Okay? And remember, when you get a full spectrum, you're going to be given a lot of different spectrum and other data. You might as well take advantage of the points you can get quickly and easily. Next one's HNMR, and this one will get a little bit more difficult. But to start, number of signals. Okay? How many signals do we see? 2 signals, which means 2 unique hydrogens. So we could again go through and write that out. 2 unique hydrogens. Okay. Next part of it, we want to figure out the chemical shift. Okay, the chemical shift for hydrogen NMR is 0 to 14 parts per million. So we can look along that bottom axis and see the overall range that we're evaluating with our chemical shifts. Okay. We could then go back to our tables and say, where do these things fall? That 0 to 2 range, we're probably looking at alkanes, which means our hydrogen is probably bound to a carbon. That next signal falls in our 2 to 6 range. That 2 to 6 range to me is way too difficult to interpret, not worth the effort. I would write it as H question mark. I have no idea what it is, but there's a hydrogen there because I have that peak. Okay? That's all I can get out of the chemical shift. So again, it doesn't really seem like that much, but we can build on this from each of our individual spectra to try and figure out what the overall result is. Whoops, that was too fast. Let me come back there. The integration said could be the peak height. It should officially be the peak area, but when looking at hydrogens bound to carbons, you can usually get away with peak height. Okay? If you look really, really carefully at this, you can see that in my simplifications, there is some overlapping here. So our integration is 2 to 3. Okay, well, what does that tell us about our structure? Well, our signal about 3 we said was a hydrogen bound to question mark, and we now know that there's at least 2 hydrogens in that signal, which means the easiest way to get 2 hydrogens chemically identical to each other is to connect them to the same atom. Okay? I've now drawn some information about that structure. What happens with our signal at 1.5 ppms? Well, again, we knew it was a hydrogen, and because of our chemical shift, we know it was a carbon. How can I get 3 hydrogens all chemically the same as each other? The easiest way is to put 3 hydrogens on a single carbon. Okay, so we started with ultimately a bunch of lines, and now we actually have 2 substantial pieces. Okay, and that's really what we're trying to get out of this. back to our integration, it can be represented with the peak height, which is kind of where I was going with this one. You might also see it as a number written underneath each peak. You'll notice that that number is not below the ppms. It's usually between the peak itself and the ppm range. You might also see it written out as I have in blue, and depending on if you have to take this class somewhere else, you might see it written out quite literally as 2H and 3H, meaning there are 2 hydrogens and there are 3 hydrogens. I tend to avoid that method, but you can see it there. Okay. That is all we can get out of the integration. So we can now move to the next piece of information, which is our multiplicity. Okay, so now we're back to the whole shebang. We've got the whole spectrum on here. So before we crack into the multiplicity, let's again address some issues here. Number one, we have that CDCl3 thing showing up again. It will show up in hydrogen NMR, shows about 7.26. If you're interested as to why you see a hydrogen showing up for a compound that does not have hydrogen, feel free to talk to me and I'll explain that one to you. The other thing that we've got is TMS, which is our 0. Okay, that's added to our sample to make sure that we have a signal showing up at 1.5. Okay? Otherwise, all we have is this signal with nothing to relate it to. We don't have a chemical shift. So TMS gives us the 0 from which we can compare everything. Okay. Last thing that I'll address before we get into the multiplicity is that you're noticing we've got that 2 and 3 again, and they've also shown these kind of weird sloped lines. Those sloped lines are artifacts from the actual instrument. The old method used to actually obtain spectra would calculate the integration as convert the area underneath the curve as an actual peak height on an integration plot. So they would actually, the computer would digitally present the integration as a height. Okay? Very rare to see now, but just in case you're aware of it. Okay? So the next part of this is going to be our fun part, our multiplicity. Okay? The number of peaks equal the number of neighboring hydrogens plus 1. So let's go through, and I'm going to label this as our red hydrogens here, and we'll call these our purple hydrogens here. So red hydrogens, let's get our information back out there. We know we have a hydrogen bound to a question mark was our chemical shift. Our integration said there was another hydrogen bound to that question mark. Our multiplicity says the number of peaks equal our neighboring hydrogens. So we would now go through and look at the number of peaks seen there. This takes a little bit of practice, but hopefully what you see is 1, 2, 3, 4, come on, 4 peaks. So we have 4 peaks equals our neighbors plus 1, which means the number of neighbors equals 3. So how can I get 3 hydrogen neighbors? Okay, again, I want to go as easy as possible to my question mark. Well, the easiest way is to put those 3 neighbors on the same atom. We got a CH3. Okay. This multiplicity actually gave us some more information. If you remember back just a few slides ago, we said that nitrogens and oxygens will hide hydrogens. That means that our question mark must be a carbon. Otherwise, it can't connect. Okay, or we wouldn't see this splitting pattern. The next thing that I like to include is a hanging bond, meaning that carbon is missing something. It needs to have 4 bonds. So I like to throw that bond on there so that I know that piece is still there. Okay. That is now what I've gotten out of the multiplicity, okay, for my red hydrogens. If we now move to the purple hydrogens, we'll again work through everything that we had for them. Based on our chemical shift, we had a hydrogen bound to a carbon. Our integration said we had 3 hydrogens. And then we would move into our multiplicity, or our splitting pattern. How many peaks do we see? again, takes a little bit of practice, but hopefully what you see is 1, 2, 3 peaks. 3 peaks equals neighbors plus 1. Our neighbors must be 2. So we go back to our structure drawing. I want to put in a carbon, because again, nitrogen and hydrogen hide. And the easiest way for me to do this, in fact the only way in this case, is to have a CH2 there. Okay. Again, I've got a missing bond, so I'll show that hanging bond outwards. Okay. I know, we just went through a whole bunch there. What information do I know about that red circle and this red circle? Really, nothing. Okay? I don't know much about that red circle at all. Okay? In the case of my 2 hydrogen signal, okay, I do know a little bit about that. That position does not have hydrogens. Whatever's attached out there can't have hydrogens attached to it. Otherwise, they would be within my 3 bond rule. So I can't have hydrogen out there. Which I know isn't a whole lot, but that is something. Okay, I know I can't have this. And this next part is where I think most students tend to get kind of a bit frustrated and misorganized with this. What we now need to do is come up with all this information that we've now collected through the Mass Spec, the IR, the carbon NMR, and the HNMR. And we now need to put them all in one unique place that's clean, not cluttered, and start to process that information. Okay? So usually what I would generate is a summary section of whatever my sheet is, or a place to compile the data. From the IR, we had a carbon-hydrogen bond. We knew they were sp3 hybridized carbons. The Mass Spec gave us a formula. The carbon NMR told us we had 2 unique carbons in the alkane class. And then our hydrogen NMR, we had these 2 general pieces that came out of this. Okay? So now what we need to do is actually draw some conclusions from this. Well, according to our hydrogen NMR, how many carbons do we have? Let's see, 1, 2, 3, 4. That's kind of problematic considering that my Mass Spec says I only have 2. So if we see this layer of duplication, we can go back to our hydrogen NMR and say, okay, did I duplicate something somehow? Is this CH3 the same as this CH3? Well, if there's nothing chemically distinct about those 2 pieces, then that means in the process of analyzing that, I duplicated it. One of those can disappear. Okay? So my next step would be that I have 2 carbons with hydrogens attached to them and a hanging bond, and then I also know, according to my Mass Spec, that I have a bromine with, again, a hanging bond. With these 2 pieces, is there any way that I can, or how many different ways are there that I can combine them? Hopefully you see that there is only one way to put these 2 compounds together, and we end up with ethyl bromide as our overall structure. Okay, and then that is our final answer. Ta-da! All of that work. Okay, 70 minutes later, we now have the arrangement of 6 atoms around each other. 8 atoms, however many atoms. Okay? So our spectroscopy is designed to go through and determine a structure from a whole bunch of individual data, which is kind of what we're doing in lab as well when we try and figure out melting points or do extractions. What we're ultimately trying to do is classify and know something about what that compound is. Spectroscopy is the ultimate form of this. Okay? Because I'm extremely tired, I'm not going to go through and stepwise through this particular example, at least not in this video. But what I will do is step through it as our very first example in class on Monday. Okay, so I forgot to get a Mass Spec for this, so I've summarized your Mass Spec information up at the top. So what we learned from our Mass Spec is that we have a molecular weight of 86 grams per mole. there are no heteroatoms, which means no bromine, chlorine, iodine, nitrogen, not there. Okay. We don't know oxygen from mass spec. Okay, so in this case, our no heteroatoms is really only referring to bromine, chlorine, iodine, and nitrogen. So not present. Those aren't present. And we can't draw any other conclusions from our mass spec about oxygen or fluorine. Okay. You should then be able to go through, evaluate your IR, evaluate the carbon NMR, and evaluate the hydrogen NMR. And hopefully what you will be able to do is to compile all of those pieces together to get an overall structure. Okay? We will work through that organization and that structural system on Monday. Okay? And I'll try and give you some pointers on Monday as well about how I would go through and organize this. I want you to see what you can come up with first, and then we'll discuss what I think is ultimately the best way to organize all of this information on Monday. Okay? If for some reason you are watching this before the exam, good luck on the exam. If you already took the exam, I hope you did better, or at least as good as you thought you did. Okay? Have a good night, and we'll see you later.